Hello everyone, today we'll talk about the problem minimum falling path sum number 2. We're given a grid with numbers written in all the cells, positive numbers, negative numbers, and we have to get from the top row to the bottom row, so going down one row each time, in such a way that the sum of the numbers on our path is minimal, and the only constraint is that we cannot go straight down. So whenever we are at a given time, for instance at this 5, then we can go to the 7, we can go to the 9. If there was something to the left of the 7 or to the right of the 9, we also could go there. But we cannot go from 5 to 8. And it can be seen here that we would like to go 1, 4, 7, but we cannot go to the 4, but we can go to the 5 and then to the 7. So essentially we cannot go straight down in any step, and we have to find the cheapest path from the first row to the last row. Now, there isn't much to think about when solving this problem. The basic idea is that we can go row by row and decide for every position in the row we're looking at what's the cheapest way to get at that very position. Because in that case, our answer would be just the minimum of all those numbers for the last row. So here, the cheapest way to get to any of those positions is exactly 1, 2, 3. For this row, the cheapest way to get to a 4 is through a 2, so that would be a 6. Let's write it down. 1, 5 would be a 6, and 1, 6 would be a 7. And again, to get a 7, we can get from a 6. So, of course, that would be 13, and so on, right? So 14 and 15. And so the cheapest route would be this 13, and indeed we see that this is the answer. We only have to return the sum. And now the two ways we can go about doing this is either to just do it naively, so go through each row and look for every position at a given row, look at all the positions above it without this one, so without one immediately, which would be, of course, O of n to the third, n cubed, because we have to go through all the positions. There are n squared positions, and then we also have to do n operations when looking at the row above. And if we want to make it faster, then we can notice that really when the row above is big, there aren't many interesting numbers in that row, because for almost any case we'll always take the minimum of that row, right? So we want to take the minimum, and the only situation that can be difficult for that minimum is if the minimum is exactly the number above us and appears exactly once, in which case we cannot take it, so we have to take the second min, which can be equal to first min, assuming that this first min appears more than once in that row. And then we can maintain those two numbers and update the next row, going through all those positions in the next row, just looking at min and second min and comparing what's above every cell. So if what's above is not equal to min, then we can take min plus our value. If it's equal to min, we can take second min plus our value. And you may be wondering why I'm talking about a solution that's essentially n cubed, and then a better solution that's O of n squared and also uses constant auxiliary memory. Let's see the code. Here above is the n cubed solution, and here's our n squared solution. And the fact is that both of those solutions, for the constraints given in the problem with n up to 200, run in similar time. The second one is slightly faster, but still, when I saw that the constraints were 200, right, so one dimension is 200, then 200 to the third is not even 10 million. So it should be easy to pass just going n cubed, especially a simple n cubed like this, where we just take minima of some contiguous portions of the arrays and updating the position based on that minimum. So this is very short code, this is very fast, those operations are simple, and it passes well within the time limit. So let's talk about it. We just go for every position, we take the minimum of what's to the left of it, maybe empty, and what's to the right of it, also maybe empty. From the row above, we return the minimum of the last row. And in the second solution, we also return the minimum of the last row, so we'll still be modifying this grid that we're given. If we're unable to modify it, we can just keep one row or two rows, depending on our implementation, that would maintain the solutions for the previous row and for the current row, or perhaps only for the current row, or perhaps we can also only maintain those two minima from before and also maintain only some candidates for the new minima from the new row. But we're not being told that we have to preserve this grid, so we might as well just write over it. And the key idea here is, of course, to use those two minima. So we want to write a function that takes a list and returns the minimum and the second minimum from that list. We can implement it, however, in whatever way we like. I basically just do it the most obvious way, so I keep a two-element list, and whenever I see a new element, if it's better than the first, so it's better than the min, it's smaller than the min, I push the min to the right and add it as its new min. Otherwise, if it's smaller than the second min, then it becomes the second min, and then I return those two numbers. And so we go through all the rows except for the first row. We take those two mins, min and second min, and we either add the min or the second min to the position row column, depending on if above our current position the first min resides. And of course, if first min and second min are the same, then we always just add that value. But if they are different, then this is the only part that cares about the constraint that we cannot go straight down. And this is of course a faster solution, but it's much more writing, and this one is actually fast enough, at least in Python.